All right. Now that Jeremy's here, let's get started. So what we were going to do was quickly finish up the last few things that we had left on our list last time, and then we'll actually move to starting the book proper. Good? Now I didn't want to rewrite out all the axioms that we had and all the theorems we already proved, so I'm just going to talk them out loud and try and remind your brain of some of the things we already proved as we go. Okay?
Yep.
So the first proof that we're going to do, we're going to do this proof right here. So, who thinks they can read what that's saying to prove? We don't remember how to read these symbols? Too dense? Too much going on? Alright, let's try it. For all x not equal to 0, so we often say for all x where x is not equal to 0, there exists, what's the exclamation point after exists?
One and only.
One and only one. There exists one and only one y, and remember, every time after we read an existential quantifier, we say such that. So, such that x times y equals 1. So for all x where x isn't 0, there exists one and only one y such that their product is 1. So for each number, there exists one and only one other number I can find to make their product 1, as long as the number we're talking about isn't 0. Because 0 times anything is never equal to 1. It's always equal to 0.
Yeah.
So outside of 0, we're going to prove that this is always the case. Give you some intuition. What if the number I'm talking about is 7? What is the one and only one y I can multiply this by to make the product equal to 1?
1/7.
1/7. 1/7 is the one and only one number I can multiply it by to make the product 1. What if my number here is pi?
1 pi.
1 pi?
1 over pi.
1 over pi. Right? Pretty simple, pretty easy to find that number. Okay. So that's what we're going to prove. We're going to prove that there's one and only one number that satisfies this. So, proof of, I'm not going to rewrite out this statement right here, but here's the statement that we're proving. Alright? The way I'm going to prove this statement to be true is I'm going to do a proof by contradiction. So I'm going to assume, now remember this, by way of contradiction. So assume by way of contradiction that there exists some other number, what should we call it? Y prime. Y prime? First we need to let our x's and y's, sorry. So 1. Let x in R, so let x be any real number, let x in the real numbers. This fancy symbol means all real numbers. That fancy symbol means in case you can't see it very well, it's like a C with a line, in. Okay, so let x in R means let x be any real number. Comma, and, sorry, let x and y be real numbers, so let x, y, in R such that x is not equal to 0 and x times y is equal to 1. Okay, now we'll do our contradiction. Assume, by way of contradiction, that there exists y prime in R such that x times y prime is also equal to 1, and y prime is something different from y. You with me so far? So we're assuming that there is some other number out there called y prime, such that when x is multiplied by y prime, we also get 1. And y prime has to be something different from y. It doesn't matter that I use a symbol y prime right there. I could have called that symbol whatever I want. Sometimes we get confused by symbols and think we have to use a particular symbol. So maybe just this once will be a little bit absurd. We're going to call it smiley face. Just to help get it into your head, what symbols we use are utterly irrelevant. We just typically use symbols that are nice. And smiley face isn't a very nice symbol, but just to make it clear to you, that the symbols don't matter, we'll use smiley face. So assume by way of contradiction that there exists some other number we'll represent with smiley face, such that x times smiley face is equal to 1, and smiley face is a number different from y. They're not the same number. Okay. And we're going to show that this is impossible. I'm going to show that, in fact, smiley face is y. And that's going to be my contradiction. With me? Mm-hmm. Okay. So then I know that smiley face is equal to smiley face times 1, right? If I have a smiley face, then I have one smiley face.
Right.
You with me?
Yep.
And 1 is the same thing as x times y. You see that? So, this is equal to smiley face times x times y. Right? Mm-hmm. Now I'm going to use commutativity and dissociativity all in one go. This is the same thing as y times x times smiley face. When we're doing multiplication, we can reorder the terms and we can put the parentheses wherever we want. That was using axiom 1 and 2 from what we had last time. Oh, not 1 and 2. 5 and 6. But you good with going from this to this? Just moving the terms around? Okay, now what is x times smiley face? 1. By way of contradiction, assume that there exists some smiley face such that x times smiley face is 1. So x times smiley face is 1. So this is the same thing as y times 1. What is y times 1?
Y.
Y. By our axiom about 1. Anything times 1 is equal to y. 1 is a multiplicative identity. So I just showed that smiley face is equal to y. Contradiction. I said smiley face isn't equal to y, and then I said smiley face is equal to y. That's contradiction. Both those statements can't be true. Therefore, our assumption that there exists some smiley face that satisfies this condition is false. So therefore, smiley face does not exist. Therefore, no such smiley face exists. And we're done. Have to fill in square. Alright. Any questions on that proof? Everything makes sense? It's kind of coming back to the stuff we've been doing so far?
I have a question.
Go ahead.
So do we have a theorem where if you have x times something is equal to x times another thing, then those two things are equal, right? Like, we have that theorem? Or have we not proved it yet?
If x times a is equal to x times b, then a is equal to b.
So we have that, right?
We didn't use that.
No, but we have that theorem.
I don't know that we proved that one explicitly. We could prove it. We did it for plus. I don't remember about times.
Okay. Oh, well, I'm just wondering if for this proof could we also say that because x times y is equal to 1 and x times smiley face is equal to 1, then x times y is equal to x times smiley face?
Yes. Yep.
Okay.
That's another way that we could have done it. Point out what she's saying there. Assume that we have this theorem. Assume that we know if x times a equals x times b. Pretend that we already proved that that implies a is equal to b. So what she's saying is that if you have smiley face times x is equal to 1, and y times x is also equal to 1, then you have smiley face times x is equal to y times x. Now use this theorem up here to cancel out the x's on both sides, and you get smiley face is equal to y. Another way to prove it. There is not one way to prove as a general rule. There's tons of ways to prove, and you find out as you go on in mathematics that the way people like to go about proving things comes down to a manner of a style. How some people prefer to think about problems. So there's a lot of, well, doesn't matter. That's going down the road. Anyways, any other questions? Good? Okay, so we proved this top one. Okay, so what did we just barely prove? We just barely proved that for any real number you choose, as long as it's not 0, there exists one and only one number I can multiply it by to get out the product 1. You with me? So since there's one and only one number that does that, we can name that number. And so x to the minus 1, with this minus 1 up here, is what we're going to define that number to be. What is x to the minus 1? That is the magic y I can multiply x by to get 1. This is very similar to how we define negative x. What is negative x? It's the one and only one number I can add to x such that x plus negative x is equal to 0.
Yeah.
Negative x is the one and only one value I can stick here such that x plus that value equals 0. That was our definition for negative x. Now we have a definition for our multiplicative inverse. What's x to the minus 1? That is the one and only one number such that x times that number gives me 1. X times its multiplicative inverse gives you the multiplicative identity. X plus its additive inverse gives you the additive identity. These are basically saying the exact same thing. Or they're very similar definitions, I mean. Right?
Yeah.
And so now let's come back and connect that with some stuff that we were already saying. If I said 7 times what magic number is equal to 1, what's the magic number we put in here? 1/7. And another way that we can represent that value is 7 like that, with a minus 1 up there. And now some of you from earlier classes might have memorized some rule that, oh, if the exponent's negative, you can move it to the denominator and put it down like that. Comes from this definition.
Interesting.
So these say the exact same thing. 7 times 1/7 is equal to 1. 7 times 7's multiplicative inverse is equal to 1. Those both say the exact same thing. While you're more comfortable with this notation is actually a lot cleaner. Makes it very clear what you're saying. 7 times its multiplicative inverse. Good?
Yeah.
Okay. And now that we have multiplicative inverses defined, you notice now we can start defining fractions. So far, what we've had defined were, well, we'll get to fractions when we define division. So we'll hold off on fractions for a second and just prove some things about these really quick. So now we have an additive inverse and a multiplicative inverse well defined. Okay, so the next thing that we're going to prove is the multiplicative inverse of a multiplicative inverse gets you back where you started. This is very similar to a proof we already did. The proof we did is negative x is equal to x. The additive inverse of the additive inverse of x is x. The multiplicative inverse of the multiplicative inverse of x is x. They say the exact same things almost. Makes sense what we're trying to prove? So let's prove that really quick. Proof. We're going to prove that x is equal to x inverse. Okay. Let's see. Well, I'll just do it this way. Okay. We won't write out all the words this time. I'll just show you the algebra part since I'm in a fairly tight space here. So first off, x inverse is equal to 1 times x inverse, right?
Yeah.
Take it, multiply it by 1. Did I change it? No. 1's a multiplicative identity. When you multiply by 1, you get back the exact same number. Okay. Now notice, coming back up here from how we defined it, let me just rewrite it really quick. By definition, x times x inverse is equal to 1. That's the definition of what that symbol means for any x, right? As long as x isn't 0. I probably should have said something, let x not equal to 0. This is only true if x isn't 0. Because 0 inverse is undefined. You can't talk about the multiplicative inverse of 0. Up here, it was for all x where x isn't 0, there's a multiplicative inverse. So multiplicative inverse of 0 doesn't make sense. Outside of that makes sense. So we're assuming x is some number not equal to 0. Okay, so x inverse is equal to 1 times x inverse. You with me?
Mm-hmm.
Now I'm going to rewrite that 1 like this.
Yep.
So if we rewrite the 1 like that, then we have x times x inverse times x inverse, right? Now I'm going to group this x inverse with this. You with me?
Mm-hmm.
So that is equal to x times, maybe I'll put parentheses like this to try and make it more clear. x inverse times x inverse inverse. Follow that?
Yeah.
Now think about what this number is right here, this whole symbol. What does this whole symbol represent? Maybe look up here. What does this whole symbol represent? This represents the multiplicative inverse of this thing. Right? We're talking about the multiplicative inverse of whatever I put in here. It happens that what I put in there was x, the multiplicative inverse of x. Who cares? It doesn't matter what I have in there. Whatever is in here, when we put this minus 1 out here, we're talking about the multiplicative inverse of whatever's in here. I happen to use this symbol here. I could have replaced this symbol with smiley face and still have been just fine. You with me? So then, I know that this symbol, whatever it is, I know it satisfies the property that x inverse times x inverse inverse is equal to 1. This thing is the multiplicative inverse of whatever's inside of it. So if I take whatever's inside of it, which is x to the negative 1, and I multiply it by this thing, then I get 1. Does that make sense?
Yep.
So x inverse times the inverse of x inverse is 1. This whole thing right here is just 1. So this is all equal to x times 1. And then what is x times 1?
Just x.
Just x. So I just really showed that x inverse inverse is equal to x. And the whole crux of the proof was understanding these two things, these two statements. X times x inverse is equal to 1. You need to understand that. And you need to understand that x inverse inverse is equal to 1. I think that this is the crux of it. If you can wrap your head around this, the whole proof comes together. And it's true no matter what symbol you put there. Let me do it one more time. Doesn't matter what you replace that with. Up here we happen to replace it with x inverse. On this line we happen to replace it with just x. Doesn't matter. As long as it fits into this format, some symbol times that same symbol with a minus 1 there, it comes out 1. As long as the number wasn't 0. We good?
Yeah.
Okay. It's easy to get lost in all the symbols and lose track of what the symbols are saying. Okay, so that takes care of that proof. Let's move on now to this one. Now this one is an interesting one. You can reverse that as well. This one is a fairly interesting one. And why is it interesting? Let's go back to its counterpart when we were talking about negative numbers. We showed that negative x times y, the additive inverse of a product, was the additive inverse of just one of the terms. When you take the additive inverse of the product, you only applied it to one of the terms.
Yeah.
Now we're going to prove that if you take the multiplicative inverse of a product, you apply it to both of the terms. So it's a little bit weird. A little bit interesting that that's how it is.
Why is that the case?
Well, we're going to prove it.
I mean, I get that, but intuitively, why does that? Why should that make sense?
Well, there's no reason that a negative number and a multiplicative, there's no reason that an additive inverse and a multiplicative inverse are identical. In fact, we know that they're not identical. They have different rules. So they're going to behave differently. But a lot of the times they're going to behave the same. So sometimes they behave the same, sometimes they behave differently. And so I'm just trying to point out when they're the same and when they're different. And why are they different? Because they're set up differently. I mean, I don't know how else to say it.
How does an exponent, so 2 to the negative 1, affect both of them versus?
Well, we haven't really talked about exponents yet.
Oh, I see.
That's just the symbol that we're putting there to say it's multiplicative inverse. Just a little minus 1, a to the minus 1. We know later how to think about that as an exponent.
Yeah.
Right?
Do we define that in this class?
I don't think we'll have a rigorous definition for an exponent. It's kind of a calculus concept.
Really?
Yeah, it can be a bit involved. Because oftentimes when you're trying to prove things involving exponents, you need to use inductive proofs. And that's a bit much to ask from an algebra class. I don't know, maybe the author gives us one. We can do it for natural numbers, pretty straightforward. But outside that, it can get kind of complicated.
Okay.
And so we'll rely on intuition. Anyways, so when we took the additive inverse of a product, it was the same thing as the additive inverse of the first term times the second term. Now what are we going to prove? We're going to do a proof that if you take the multiplicative inverse of a product now, that is actually equal to the multiplicative inverse of the first term times the multiplicative inverse of the second term. Good?
Yeah.
All right. Well, a couple different ways we could do this. Let's start by writing it out. One, let x, y in R such that x is not equal to 0 and y is not equal to 0. I think that's the only thing we need to require. Because if x or y is 0, then their product is 0, and the additive inverse of or the multiplicative inverse of 0 is undefined. Doesn't exist. It doesn't happen. Okay, so let x and y in R such that x, y is 0. Okay. Observe. How do I want to do this? The way I'm thinking about doing it is I'm thinking about saying, what is x times y inverse? X times y inverse, that is the unique solution to the equation. X times y, well, oh well. X times y then times x times y inverse then is equal to what?
1.
Is equal to 1. Now, x times y inverse is the only number that satisfies this equation. We proved that this is unique. There's one and only one number I can plug in right here, such that x times y times that number gives me 1, right? X times y over here, even though I represent this as a big symbol, this is just one number. So a number times its inverse is equal to 1. And furthermore, there's only one number I can plug in here that makes it equal to 1, right? So if I can show that x times y times, put bracket here so you see why I'm substituting, times x inverse times y inverse, if I can show that this is also equal to 1, so if I can also show that, maybe put parentheses here to make it real clear, if I can show that x times y times this other thing is also equal to 1, then this other thing is also a multiplicative inverse. Because it took my number and it turned it into 1. What is a multiplicative inverse? It's a number such that when you multiply it by it, you get 1. So I know that x times y has only one multiplicative inverse. If I can show that this is a multiplicative inverse, then this is the only multiplicative inverse. So it is this. They're the same. You with me? Mm-hmm. Okay. So let's just show that. So x times y then. X times y times x inverse y inverse. You with me?
Yeah.
Now we're just going to use a bunch of associativity and commutativity. I'm going to group x with x inverse and y with y inverse. I can rewrite this whole thing as x times x inverse times y inverse. Right?
Yep.
And what is x times x inverse?
1.
What is y times y inverse? 1. What's 1 times 1?
1.
You sure?
I hope so.
Okay. So, since when I took x times y and I multiplied it by this thing, since taking x times y and multiplying it by this thing produces 1, this thing must be a multiplicative inverse of x times y. But there is only one multiplicative inverse of x times y, which is this. So this must be the same thing as that. You see the logic there?
Yes.
Okay, so therefore, blah, 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 therefore this statement. Therefore the inverse, the multiplicative inverse of x times y is x inverse times y inverse. Follow the logic there?
Yeah.
Okay. And then finally, our definition for division. So, do you remember our definition for subtraction? We said a minus b, we define that to be a plus b's additive inverse. A subtract b, we define that to be a plus b's additive inverse. You with me? So similarly, we're going to define x divided by y to be x times y's multiplicative inverse.
Okay.
So for all x and y, where y is not equal to 0, x divided by y is the same thing as x times y's multiplicative inverse. Why can't y be 0?
Because then it would be undefined.
Because then it's undefined, because 0 doesn't have a multiplicative inverse. There is no magic number that I can multiply 0 by. There's no number I can put in there, multiply 0 by, such that the product gives me 1. We already proved that anything times 0 is 0. So 0 doesn't have a multiplicative inverse. So if I say 0 inverse, that's bad, that's undefined. That's like using this word in the English language. It's not a word. Alright. So one more proof using this definition of division, and then we'll start the book proper. So proof. We're going to prove that x plus y divided by z is the same thing as x divided by z plus y divided by z. You with me? Alright, so let's just do the proof. So x plus y divided by z, using our definition, what is this equal to?
X plus y times
Z.
The numerator times the multiplicative inverse of the denominator. So we just write the numerator, that's x plus y, times the multiplicative inverse of the denominator.
Okay.
Right? Now what do I know I can do with this?
Can't you distribute?
Distribute. I'm going to distribute this across those. Go back and use axiom 9. Axiom 9 was our distribution axiom. If I have a number times a sum, that equals to the sum of the two products. That equals to the sum of this times this and this times this. So this is equal to x times the inverse plus y times the inverse. Right?
Yeah.
Now, by definition of division, looking at it this way, right here, a number times a multiplicative inverse is the same thing as a number divided by that number. So x times z multiplicative inverse is the same thing as x over z. Right?
Yep.
And y times z inverse is the same thing as y over z. We follow that?
Yeah.
Okay. So that's as far as we're going to go with those. That was just to give you a taste of the foundations for the field that we're developing and how we could rigorously start developing these things. Now we're going to actually start the textbook, and we're going to use much higher reasoning in the textbook, meaning we're not going to be near as rigorous, and we're not going to prove things out near as rigorously as we've been doing so far. So what this class has kind of done in terms of difficulty to understand, if we were to write as difficulty to understand as we've been doing, it goes kind of like this. That's how the class is. Starts out pretty easy, talking about basic logic. Logic gets pretty complex pretty quick. Here we're talking about the axioms. Things kind of lighten up as we're proving some of our improofs, and it feels like what we're talking about is going to get a lot easier and then hard when we finally reach the end of the class again. And that's kind of how the difficulty level of classes like this go. So things should start easing down and getting into easy territory now. Is that encouraging?
Yes.
All right. So now we start out with chapter 1 of this book, which the first chapter is called Basic Review, because the author assumes up to taking this class, you have already done some basic algebra before, you're already familiar with arithmetic. If we cover a concept while we're going through chapter 1 that you are fuzzy on, it is just fine to say, can we do more of that, more examples of that, go further into that, anything like that, and get a better understanding. Second thing you're going to notice I do a lot is in my examples, to help give you intuition for what we're talking about, I'm going to jump ahead in the class and reference topics that we haven't discussed yet. Like, we'll talk about what a square root is, but I'm counting on the fact that you already know about square roots, so I can use that in an example. So none of my proofs will jump ahead, but our examples will often jump ahead in the class to concepts that you might have already come across before. Does that make sense?
Yeah.
Okay. So you'll notice that we do that a lot. So don't be scared just because you see something in an example that we haven't yet come across. Okay. So the first discussion that the author has in this book is a conversation about numbers. About numbers and the fact that what we're interested in this class are sets of numbers, and in particularly the notion that a number is an abstract element. Stressing the point, it's an abstract element. What do we mean by the fact that a number is abstract?
It's not something physical or concrete.
It's not physical or concrete. It has no physical representation in this universe. This is not one. This is a finger. One is not physical. You can't poke one. You can't smell one. You can't touch one. It's abstract. It's not a physical quantity in this universe. Can't touch it. So they're abstract elements. Now we're going to have number symbols that we use in this class all the time. And number symbols are what we use to represent a number. And we often call the number that a number symbol represents its value. So here's a bunch of different number symbols. 5, 3 plus 2 in parentheses, square root of 25, the word 5. Those are all number symbols for the same value, 5. Right? Nothing weird there? Okay. Now, in writing our numbers, we use a base 10 system. What do we mean by a base 10 system? It means our system has only 10 symbols that we use to represent numbers. We use a 0, a 1, a 2, a 3, a 4, a 5, a 6, a 7, an 8, a 9. And these are all the symbols that we use to represent our numbers.
Okay.
Good? And you understand how those symbols count? You start listing out the numbers, 0, then you do 1, then you do 2, dot, dot, dot. Eventually you list the number 9. Then after 9, you go back to our 1 and put a 0 after it. And then you replace a 0 with a 1, a 2, a 3, 4, 5, etc. Pretty sure you know how to count up the numbers, right?
Hope so.
Okay. Now exponents, when we have a positive whole integer here. So when we have a positive number there, like a 5, then a to the 5 means a times a times a times a 5 times. If I have a to the n, that means a times a times a times a n times. So when you see 2 to the 5 here, that means 2 times 2 times 2 times 2 times 2. Right? That symbol multiplied together 5 times for any positive whole number you put up there. Meaning 1, 2, 3, 4, 5, 6, etc.
How about negative?
Don't worry about it. We're not there yet.
Okay, will we get there?
Well, of course we'll get there. But it'll be the same thing. We can jump ahead if you want. What do we mean by 2 to the negative 5? We mean this is the same thing as 2's multiplicative inverse 5 times.
Okay.
And so that's the multiplicative inverse of 2 times the multiplicative inverse of 2 times the multiplicative inverse of 2. Or in other words, this is equal to 1 half times 1 half times 1 half times 1 half times 1 half. The multiplicative inverse of 2, 5 times. That's all that means. Another way that you've seen that written, notice that that's 1 over 2, where 2 is multiplied 5 times. So we could also write this as 1 over 2 to the 5. And so you were told, if your exponent is negative, just rewrite your number in the denominator, making your exponent positive. That's where it all comes. But we'll have a lot more to say about exponents as we go further in the class. Okay, so now a decimal number. Do we know what a decimal number is?
Just part fraction number.
It's a collection of these symbols, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, with a decimal point somewhere in between them. Could be at the end, could be at the start, but somewhere. Good?
Definition.
That's the notion. We're not going to give precise definitions. We'll give some precise definitions to some things, but I told you we're going to talk on a higher level. Now we can define each decimal number, so I won't give you a proper definition for a decimal number, but I'll now show you how you can give a proper definition to a decimal number like this, in terms of things we've already talked about. So now how can I define a decimal number like 361.24? Notice that it's composed of just these symbols with a decimal point somewhere. How can I define a symbol like this? I can now define this as, we take the first one, 3 times 10 to the 2, or in other words, 300, right? Plus 6 times 10 to the 1, or 60, plus, I can write this as 1 times, we'll leave it as 1 right now. I don't want to say that 10 to the 0 is 1. So we'll just leave that as a 1. Plus, how am I going to represent this one?
-1. 10 to the -1.
2 times 10 to the -1, or 2 over 10. 2 times 10 to the -1, same thing. And so we call that the tenths place. So this number has 2 tenths. Plus, and then we do 4 over 10 squared, or 4 times 10 to the -2, same thing. And that is how we can define this number. And notice that everything we have over here are notions we already have defined. Everything over here are just integers. We already know those integers, and we already talked about how to define each of those integers, right?
Yeah.
For example, we define 3 to be 2 plus 1. We define 2 to be 1 plus 1. And then what's our definition for 1?
0.
Bad question. 1 gets its meaning from the axioms. It's not defined. But, so everything we have here, all the symbols we have here, we now know about. We now know what it means to plus. We now know what it means to have 10 squared. We now know what it means to divide. So I re-express this in terms of only things that we've already talked about in this class, and that we have well defined. Right?
Yeah.
Everything on this side, you should know exactly what it means. And so now that's what this decimal number is. And so now you can give the definition for any decimal number, right?
Yep.
Okay, so those are decimal numbers. We have roughly 3 different types of decimal numbers that we talk about. The first type of decimal number that we talk about, we call a terminating decimal number. So 5/4 is an example of a terminating decimal number. If I write this as a decimal, we can write this as 1.25, and then the point is, the decimal doesn't go on forever. It terminates.
Yeah.
Now we also have the notion of a repeating decimal number. If I were to write 1/3 as a decimal number, that's 0.33333. When you put a line above it, that means just repeat that over and over again. So 1/3 is equal to 0.3333 ... If you're just repeating threes, you put a line above it, and that means 0.3 going on forever. Make sense? This is what we call a repeating decimal, because there's some pattern in the decimals that just repeats forever. Another example would be the number 1/7. 1/7 is 0.1428971428971428971, 1428971428997, repeating forever. So it's also a repeating decimal. So repeating decimal, terminating decimal. You with me so far?
What happens if it doesn't follow a pattern but goes on forever?
Yeah. What is that decimal called?
Okay, we'll get to that one here in a second. Before we get to that one, I want to show you how every terminating decimal can be represented as a repeating decimal. Every terminating decimal can also be represented as a repeating decimal by, when you get to the end, put a 0 there, repeating. Right? If I do repeating zeros after that, that doesn't change anything.
Yeah.
Because then I'm adding 0 thousandths plus 0 10,000ths plus 0 100,000ths plus 0 millions, etc. It's not going to change my number adding 0 to it. You with me? So far, our decimals can be split into repeating decimals, and now we have a notion of non-repeating decimals. Decimals that go on forever, but there is no pattern. So with terminating decimals, those can go on forever with a pattern. For repeating decimals, those can go on forever with a pattern. Decimals that do not go on forever with a repeating pattern are non-repeating decimals, is what we can call them. An example of a number like that would be the number pi. Pi is a non-repeating decimal. 3.41159, blah, 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 blah. You write out the first 10 trillion digits, there's no repeating pattern.
Yeah.
Make sense? Another example of a non-repeating decimal would be the square root of 2. Going to be 1.41, I don't know, blah, 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 blah. It goes on forever, never repeats. There's no repeating pattern in its decimal points. You with me?
Mm-hmm.
We have another name for all these decimal numbers that are repeating. Turns out those are also rational numbers. And the ones that don't repeat are also irrational numbers. And we'll make sense of that here in a second.
Is there a difference between endless decimals and just decimals?
A decimal number, every decimal number, like 1.25, can be represented as an endless decimal number by just putting the 0 there.
I'm just wondering why you have them two different categories. Is there a difference between them or are they the same thing? The decimal and
We can
endless.
rewrite everything in this category in this category. We can't rewrite everything in this category in this category. I can't represent 1/3 as a terminating decimal number.
I'm not talking about terminating and repeating, I'm talking about the overhead general. You wrote decimal and endless decimal in two different categories. I'm wondering if they're two different things.
Endless decimal, here's an endless decimal. Endless, I had to put the 0 there to make this an endless decimal.
Yeah, but it's normally a terminating.
Every decimal number can be represented as an endless decimal.
Okay,
Not every endless decimal can be represented as just a decimal.
okay.
Okay, good question. Although typically when we say decimal from here on out, we mean endless decimal. Good? Anything else before we continue with these?
No.
Okay, so the point being that so far for every real number, there's two different ways we can write it. We can either write it as a repeating decimal number or as a decimal number that doesn't repeat, non-repeating decimal number. And those are the two ways we can write every real number. Now, it is beyond the scope of this class, but it turns out that every real number can be represented as an endless decimal number. We won't prove that, you'll just have to take my word for it, that's a fact. And so this splits all the real numbers into two categories, the ones that are repeating decimals and the ones that aren't. Now before we get to what exactly a rational number is and the definition that we use for rational, because when people think about rational, they don't think about, oh, that's a repeating decimal number. That's not how most people think about rational. So we'll give you the definition that we typically use for rational and show you how it's connected with this. But before we get to rational, first let's talk about some common sense that are just talked about all the time in mathematics, so let's make sure that we understand them before we move on. So the set of numbers 1, 2, 3, 4, 5, etc., going on counting like that forever, you get the pattern? We call these numbers, the author calls these numbers the natural numbers. Sometimes some authors define it to have 0 in there. Some don't. And I think for this author, he just does 1, 2, 3, 4, 5, etc. So I'll follow the author. Go ahead.
In discrete, he defines it with the 0, right?
In discrete math, it has a 0 in there.
Yeah.
I like having the 0 in there because when you construct these from set theory, the empty set is 0, and there's no reason to exclude it. When you're doing the empty set, the set containing the empty set, etc.
Yeah.
So I personally like having 0 in there, but I'll try and follow the author on this. And then this z here with this extra line. So that was supposed to be an n with an extra line. That's our symbol for the natural numbers. This z here with an extra line we use to represent the integers. And the integers are all the negative whole numbers, all the positive whole numbers along with 0. And I think you already have good intuition for what those are. But in case you don't, that's what they are. So from here on out, if I say a natural number, I'm talking about one of these. If I say an integer, I'm talking about one of these. Any questions on that? Good? Okay, so now we're ready for our definition of what exactly a rational number is. Definition 1. A real number x is said to be rational provided that for any two integers p and q you pick, as long as q is not 0, x is equal to p over q. So if I can find two integers p and q such that x is equal to p over q, then x is a rational number.
Yep.
So 1.25 is a rational number. How do I know? Because I can represent it as 5 over 4. Since I can represent this as an integer over an integer, it's rational. 0.333 going on forever is a rational number, because I can represent that as 1 over 3, where both those are integers. Pi halves is not a rational number. That is not an integer over an integer. Pi is not an integer. It's 3.14159 going on forever. It's not in the set of integers. This is not rational. Feel like you got it?
But yeah.
Question. I'm going to start writing some numbers up here. I want you to tell me whether or not they're rational. Let's see. Let's do 3/4. Is that rational?
Yes.
Yes. Okay, let's do 1.5. Is that rational?
Yes.
How do you know?
Because you can put it as 3 over 2.
3, yeah, it's 3/2. Wonderful. All right, let's try another one. 7.
Yeah.
Yeah?
7/1.
Yeah, that's the same thing as 7/1, isn't it? I found two integers such that when you divide them, you get that number. Notice, you don't always have to be, we could have also done, since I can write this as 28/4, that's another way I can show it's rational. Right? All right, let's try another one. 0.
Yeah. Because 0's not in the integers. It is.
Yeah.
Can I represent that as a fraction of numbers?
Yeah.
What?
0/1.
0/97, more like. We can't divide by 0. We definitely could divide 0. 0 divided by 97, that's perfectly fine, that's just 0. 97 divided by 0, that's a whole nother story. Because remember, what is 0 divided by 97? If we think about its exact definition, what is 0 divided by 97? That is equal to 0 times the multiplicative inverse of 97. Which is the same thing as 0 times 1/97. Right?
Yeah.
And what is 0 times anything?
0.
0, which is a number. So that's perfectly defined. So you can do 0 divided by numbers, that's perfectly fine. You can't divide by 0. Because when you divide by 0, if 0 is in a denominator, then we have to talk about 0's multiplicative inverse. And it doesn't have one. Okay. So is 0 rational?
Yeah.
Yeah? Okay. Let's try another one. Is that a rational number?
No.
Yeah.
We got yeahs and no's.
Yes.
How do I know that's a rational number? Because 3 pi over 2 pi is the same thing as 3 halves. The pi's cancel on top and bottom. In case you know that algebra. Right? So an irrational number over an irrational number can still produce a rational.
Weird.
Can I take a product of two irrational numbers and get a rational?
Sure.
You think so?
I,
Can you give me an example?
Square root of 2 times square root of 2.
Square root of 2 times square root of 2.
yeah.
Square root of 2, that's irrational, but the square root of 2 times the square root of 2 is equal to 2, which is equal to 2/1. So it's rational.
Interesting.
Alright? So don't be tricked by the numbers and think about the actual value that they represent before you fall into the hole of calling it irrational. Okay, so I think you got a sense for what a rational number is. Feel like you're good there? Can be represented as a fraction of two integers. If it's possible to represent that way, it's a rational number. Now we use this fancy Q for the set of all rational numbers. It's Q with an extra line. This just means the set of all rational numbers the same way that Z with an extra line means all integers. And obviously you use a Z when you're talking about integers, and obviously you use a Q when you're talking about rationals. Right? No, it makes no sense. You just have to memorize it. Good?
Yeah.
Yeah, don't say things make sense when they don't make sense. There's no reason to use Q. There's nothing special about Q for rationals. But R was already taken for reals. And what comes after R? S. So maybe let's look in front of R. Q. Alright. Now, definition of an irrational number. What do you think an irrational number is?
Not a rational.
It's a real number that's not rational. That's what we mean by an irrational. So a real number that is not rational is said to be irrational. So all the real numbers can now be split into rational numbers and irrational numbers. Every real number is one of those two categories. It's either rational or it's not rational, meaning irrational. Good?
Yes.
Okay. So, let's move the camera now so I can write over there and hopefully, let's see there. I can see it all.
Yeah, you're good.
Okay, yeah, don't let me go over there without moving the camera, in case we get over there. So, later in this class we'll prove this, but I want to give you a notion of it right now. I want to give you a notion of why every repeating decimal number is in fact rational. So that's the next thing I want to give you an idea of. So, give me any repeating decimal number.
1/3.
Something harder. I mean, show that it's rational. So if we're talking about like 24.769 repeating like that. Let's show that this is actually a rational number. You with me?
Yeah.
Okay, so I'm going to say x is equal to that number. Good so far?
Sure.
Then 100x, sorry, we need 1000. Sorry, let me shift it some. So x is equal to, I don't even remember what I wrote, 24.769, something like that. Okay, we're going to show that that number is in fact rational. We're going to show that can be represented as an integer over an integer. How am I going to do it? I'm going to write out what's 1000x equal to. What's this number if I multiply it by 1000?
24,769.
When you multiply it by 10, every 10 you multiply it by, it shifts the decimal place one to the right. Multiplying by 1000 is the same thing as multiplying by 10 by 10 by 10, right? So we're going to shift the decimal place over 3 times. So this is the same thing as 24,769.769, repeating. Everyone follow that? Nothing weird there? So now I'm going to do this number minus this number. I'm going to do top minus the bottom. What's 1000x minus x? 999x. If I have 1000 x's and I get rid of one of them, I'm left with 999 x's, right? Furthermore, 24,769 .769,769,769 minus 24.769,769,769, etc. What am I going to get? Well, I'm going to get 247. 6 minus 20 is going to leave me with 40. 5 minus 4, or 9 minus 4 is going to leave me with 5. What's going to happen with my decimal points though?
Go away.
They're going to perfectly cancel out. The decimal points here is 0.769,769, or 0.769,769,769. The decimal points here is 0.769,769,769. And so those decimal points minus those decimal points gives me a big old repeating 0, right?
Yeah.
Everyone follow that? Nothing weird? Okay, so 999x is equal to 24745. The 0 repeating, we can erase that and we didn't change our number, right?
Yeah.
Okay, so what do I do then? I divide both sides by 999. So then x is equal to, maybe make it very clear what I'm going to do. What am I really going to do? I'm going to multiply both sides by 999 multiplicative inverse. So if this is equal to this, then 999 times x times 999's multiplicative inverse is equal to 24745 times 999's multiplicative inverse, right?
Yeah.
And multiplying by the multiplicative inverse is the same thing as putting it in the denominator. Well, let's rewrite this one. I can put the 999 together with 999's multiplicative inverse, and what does this times this give me? 1, right? So over here I'm left with 1 times x is equal to, this I can rewrite using our definition of division, that's probably now off the camera, as 24745 divided by 999. That's what we meant by division. 24745 divided by 999 was the exact same thing as 24745 times 999's multiplicative inverse, by definition. And so 1 times x, that's the same thing as x. So if you take your calculator and you do 24745 divided by 999, you will get 24.769769,769 on your calculator. Make sense?
Yeah.
And so this was just doing an example, but this gives you a sense of how you can show any repeating decimal is in fact a rational number. Just see how many decimal places are repeating, and if there's 3 of them, you multiply by 1,000. If there were 4 of them, I multiply by 10,000. If there were 5 of them, I multiply by 100,000. You with me? We kind of already did one of these last time. We looked at 0.99999 repeating, and we showed that that one was a rational number. Let's remind ourselves of that one. X is equal to, I'm just going to get rid of this thing right up this line. 0.9 repeating, right? What rational number is that?
Just one, right?
Just one, but we got to prove it. So multiply both sides by 10, and I get 10x is equal to 9.9 repeating, right?
Yeah.
Now, bottom line minus the top line. 10x minus x is, whew, that's some fast algebra. All right, 9.9 repeating minus 0.9 repeating leaves me
9.
just a 9, right? And now, multiply both sides by 9's multiplicative inverse. So we do 9 inverse on this side, times, and we do times 9 inverse on this side. 9 times 9 inverse is 1 is equal to 9 inverse times 9 is 1 times x, or in other words, x is equal to 1. Or, since we wanted to write it as a rational number, 1 over 1.
Why would it round it to 1 on this one, on the other one, and keep it repeating when you do the division?
It didn't keep it repeating.
Isn't that what you said?
We got an integer over an integer.
Yeah.
True, but once you
when
divide
do
it-
that division again, you said it would bring you back to 2, 4, 7, 9, 6 repeating.
Oh, why doesn't your calculator pop out 0.999 repeating?
Yeah.
Because that's an easier thing to pop out.
Yeah. Just got right there.
Okay.
It's the same reason that every time you type this in your calculator, it pops out 5 rather than 3 plus 2 again.
Actually, sometimes, one time it popped out 3 plus 2 for me. And then I had to like mess with the 6.
Well, yeah, it's something screwed up then.
Okay.
You probably somehow had complex numbers turned on, and there's probably like an I sitting right there. Then that would make sense. But no, you can't just make your calculator pop out 3 plus 2. It doesn't know how to do that.
Do we get into those complex numbers in this house?
Yeah, we'll get into complex numbers in this class.
Okay.
Okay, so there we go, a couple examples of how any number that can be represented as a repeating decimal is in fact a rational number. So an irrational number then is a number that can't be represented as an integer over an integer. You with me? So the next thing we're going to do is we're going to do a proof. We won't do a very rigorous proof, but we'll try to give you the big idea of it. That the square root of 2 is irrational. It cannot be represented as a quotient of 2 integers. There are no 2 integers you can find such that their quotient gives you the same thing as the square root of 2. In other words, you plug the square root of 2 on your calculator, it gives you 1.41, blah, 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 blah. There's no 2 integers you can find such that their quotient gives you that same infinite set of integers. Or infinite set of decimal points. So I'm going to prove that this is not rational. So I'm going to prove this is in the rationals. No, it's not in the rationals. And so that's our symbol for not in. Square root of 2 is not in the rationals is the same thing as saying the square root of 2 is irrational. That's why you write it on paper, so that you don't have to write so many letters. Good? Okay. So we're going to prove that the square root of 2 is irrational. We're going to do this by proof by way of contradiction. We're going to do 1. Assume by way of contradiction that the square root of 2 is a rational number. We're going to assume by way of contradiction that it is in there. You with me? Now, if the square root of 2 were rational, what would we know about it? What do we know about every rational number?
You can take two integers and divide them.
That there exist two integers such that it's equal to their quotient, right? So 2. Then there exists, what do we use over here when we defined it? P and Q. Then there exists two integers, we'll call them P and Q. Then there exists P and Q in the integers such that Q is not equal to 0 and square root of 2 is equal to P over Q. If the square root of 2 were rational, then I could find two integers such that their quotient gives me the square root of 2, right?
Yeah.
And we're going to show that that's impossible.
Okay.
You with me? Then I'm going to square both sides of this equation. I'm going to multiply both sides of this equation by the square root of 2. I'm going to multiply this by the square root of 2. I'm going to multiply this by the square root of 2. You with me? What's the square root of 2 times the square root of 2? 2. So when I multiply that side by the square root of 2, I just get 2 is equal to. Now the square root of 2 is the same thing as P over Q. So I'm going to multiply, just show you what I did really quick. Over here I multiplied this side by square root of 2 again. And over here I'm going to multiply by P over Q again. But P over Q and square root of 2 are the same thing. They're equal, right? So square root of 2 times square root of 2 is 2. P over Q times P over Q is P squared over Q squared. That's what we mean by P squared. What did I mean by P squared? I meant P times P. That's what we meant. If you have a to the n, that means a times a times a, n times. If I have P squared, that's the same thing as P times P.
Yeah.
Couldn't you just say 2 though? 2 equals 2? Because P over Q equals this square root of 2. So
Oh, so you're saying plug it back in, I get 2 equals 2?
yeah.
So all I proved is that if the square root of 2 is rational, then 2 equals 2. That's not what we're after. But there isn't anything wrong with that. It's just not what we're trying to prove. And you accidentally use logic like that all the time doing proofs. That is not an uncommon thing that you just did in proving. So you always got to keep track of what you're trying to show. Okay. So then 2 is equal to P squared over Q squared. Or in other words, this is logically equivalent to 2 times Q squared is equal to P squared. You with me?
Yeah.
I skipped a thing that I want to note before I write this. Do I want to write it? Something about fractions. Again, this isn't something that we're rigorously proving. It's just giving you a sense of how we know some of these numbers are irrational. So we're jumping ahead. This is just an example to give you a sense of how we know some numbers are irrational. So calling off future algebra that we haven't used yet. But for any set of integers I have, so if I have something like 16 over 4, if I have an even over an even, I can always reduce it. And I can rewrite this as what?
8 over 2.
8 over 2. If you have an even over an even, you can always reduce it. Divide top and bottom by 2, or cancel out the 2 top and bottom. You with me? So 16 over 4 is the same thing as 8 over 2. Is that an even? Is that an even? So I can do it again. And this is the same thing as 4 over 1. Okay, now I can't do it anymore. Let's do one more just to make sure that we're clear on this. And then let's do 36 divided by 10. Is that an even over an even? Then I can reduce it. What can I reduce it to?
18 over 5.
Yeah, 36 divided by 2 is 18. 10 divided by 2 is 5. Is that an even over an even?
No.
No. So here's the point that I want to make, is that anytime I have a fraction of integers, I can rewrite it so that either P or Q is odd. I can keep reducing it until either the numerator or the denominator is odd. As long as both of them are even, I can reduce it by a factor of 2, right?
Yeah.
So, I'm going to expand upon this line, make it a bit longer. So then there's just p and q in the integer such that q is not equal to 0. The square root of 2 is equal to p over q, comma, and either p is odd or q is odd. One of them has to be odd, right? If they're even, we can just reduce it until, and we can keep reducing until one of them were odd. You with me so far?
Yeah.
Yeah.
Okay, 3. Now multiplying both sides by the square root of 2. Then 2 is equal to p squared over q squared, right?
Mm-hmm.
Which gives me the same thing, that's the same thing as 2 times q squared is equal to p squared. You with me? Now, 2 times an integer is always what? Even or odd?
Even.
Even, right?
Yeah. That's
Pick any integer you want. 17. Multiply it by 2. You get an even number, namely 34. So q squared, whatever that is, that's just an integer. And any integer multiplied by 2 is guaranteed to be even. So this side is an even number. You with me?
yeah.
This side is equal to this. So p squared has to be even. And if p squared is even, then p has to be even. Because anytime you square an odd number, you get an odd. What's 3 squared? 9, which is odd. What's 5 squared?
25.
What's 7 squared?
49.
What's 9 squared?
81.
What's 11 squared?
121.
121? Etc. When you square an odd, you get an odd. So since p squared is even, then p has to be even. So 4. Observe that 2 times q squared is even, which implies that p squared is even, because p squared is 2 times q squared, right? Which gives me that p is even. You with me so far?
Yeah.
Yeah.
Any theorems or anything for that? Or is that
Yes.
just intuition?
If we were in a discrete math class, we would be proving a lot of these things slowly as we went. I'm just relying on your intuition for a lot of this.
Would it that imply that q is odd?
Oh, well, we'll get there. And in fact, it's going to imply that q is even. And that's going to be our contradiction.
Oh, I see. I
Yeah,
see.
that's where we're going. So p is even. 5. Now, if a number is even, what does that mean? What's your intuition for a number is even?
You can divide it by 2.
You can divide it by 2, right? Is that your intuition for a number is even? Okay, 5. Since p is even, comma, there must exist some number, I'm just going to call a, there must exist some integer a and z such that p is equal to 2 times a. P must be 2 of some integer since it's even. There has to be some integer such that when you multiply it by 2, you get p. That's what it means for it to be even. How do I know 10 is even? Because it's 2 5s. How do I know 100 is even? Because it's 2 50s. Any even number can be represented as 2 times some other number. Maybe that other number's odd, maybe that other number's even. But if p is even, it's equal to 2 times some integer. That's what you mean by even.
Isn't that the definition of even?
Yes, from discrete math.
Wait, hang on. What about 2? 2 equals 2 times 1.
Can you, there you go.
2 times 1 is 1 though.
That's some crazy math.
Oh, wait, no.
Alright. So yes, any even number can be represented as 2 times a number. That's what you mean by even. If you have even teams, you have the same amount of people on both teams. If I have 5 people on both teams, they're even. Because when you take the teams together, you have 10. 5 was that magic number there. Good?
Mm-hmm.
Go ahead.
Can I use the restroom?
Peter might have a key. Yeah, he'll help you out. Okay. So, since p is even, then we can write it as 2 times some other integer. You with me? So now I'm going to make that substitution clear back up here. So then 2 times q squared, 2 times q squared is equal to p squared. What's 2a squared?
4 times a squared.
4 times a squared. So 2 times q squared is the same thing as p squared is the same thing as p squared is the same thing as p squared. What's 2 times 2?
4.
4. What's a times a? A squared. Not 2a. That's a plus a. Remember our definition for exponents. What do we mean by a to the n? If we have a 2 times, that's a to the 2. So 2q squared is equal to 4a squared. You with me?
Yeah.
Or in other words, multiply both sides by 2's multiplicative inverse, or another way to say it is divide both sides by 2, and we get q squared is equal to what?
2 times 6.
2 times a squared. You with me?
Yes.
Which implies q is even.
Yeah, let's take that one bite at a time though. So now notice that q squared is equal to 2 times a number, right? So then q squared is even, right? Since it's 2 times a number. And an odd times an odd is always odd, and an even times an even is always even. So if q squared is even, then q has to be even. So this implies that q squared is even, which implies q is even. And there's our contradiction. Because we said, way up here, and either p is odd or q is odd, right? So we knew either p or q had to be odd, but we found out, uh-oh, p's even. And we found out p being even also made q even. So they're both even. So we said one of them has to be odd and they're both even. Those are contradicting statements. So our assumption that square root of 2 is rational is wrong.
Just to know, your or is not inclusive, right? It's the exclusive or.
Or is always in the inclusive sense.
So p. Oh, sorry. Yeah, I have it backwards. No, you're
Okay. Every time we say or, we mean in the inclusive sense.
Okay.
So now our assumption, 7, therefore our assumption is wrong. Therefore, the square root of 2 is not in the rationals. Because if you assume that the square root of 2 were a rational number, then it is always represented as an even over an even.
Will we
You get an
rigorously-
infinite reduction. Huh?
Will we rigorously prove this using definitions?
No, we did that in discrete math.
Oh, so we're not going to do stuff like in discrete math. We're just going to kind of give a high level and then go with it.
We'll get a high level for a lot of it, yes. Because rigorously proving all this stuff, that's what you do in real analysis, that's what you do in calculus. When you take the axioms of the real numbers and look at their logical implications, that's calculus. In discrete math, you start with the rationals or subsets of rationals.
Yeah.
And you look at what's true for those. And since we're interested in the rationals in discrete math, we also talk a bit about irrationals, but yeah, we won't prove it like we did in discrete math. But it's something that every algebra student should see at least once. A proof that at least one number is irrational. Okay, so we proved that the square root of 2 is irrational. Talked about rational, talked about irrational. We did that. Okay, so now we're ready from the author's perspective to start talking about the axioms that we've already talked about in this class. Tired of using the whiteboard. I just don't know if we have good markers. We'll risk it.
That red one seems to work pretty good.
Yeah, it was already dying on me a little bit. We were writing over here, so you can't see the part that was dying. Is that seeing the whole board? No. Close enough. Okay, let's try and stay more centered. Oh, I hate this eraser. Sorry about that. Try the black one. Okay. So now we get to our next section. So we're still inside chapter 1. The first section was just talking about real numbers and decimal numbers. Now we're talking about addition and multiplication instead of just talking about numbers. So addition and multiplication. The author starts by saying that 1, for all x, y, and r, for any two real numbers, there exists a unique number, z, into real numbers, such that x plus y is equal to z. We don't need to put a 1 here. I'm writing kind of dense, but reading out loud, so hopefully you can follow. So this isn't something that we're proving. He's going to restate some of the axioms we already talked about. So for any two real numbers, there exists one and only one other real number. Maybe it's the same as one of those two, maybe it's different, but there exists one and only one real number, such that those two added together gives me a resulting real number. So taking two real numbers, add them together, it gives me another real number. Furthermore, it only gives me one real number. I can't do 2 plus 3, and at one moment get 5, and at another moment get 6. I always get one and only one number out from a particular sum.
Okay.
Does that make sense?
Yes.
I know notation's kind of dense, but... And we also have as an assumption for all x, y, and r, there exists one and only one other real number, we'll call it z, such that x times y is equal to z, which is saying the same thing, but now just with multiplication.
Wasn't this assumed?
Yes. So we assume that we have an operation plus and an operation times on the real numbers such that these two things are true, and then we list our axioms. And 1, here now we list our axioms. And let's see, he does commutative, associative, distributive. So he's just going to list a few of the axioms at a time and work with them as I go. So such that 1, x times y is equal to y times x. 2, x times y times z. I don't want to use z now because I used it up there. I'll just use it. Times z is equal to x times y times z. 3, x plus y is equal to y plus x. 4, x plus y plus z is equal to x plus y plus z. 5, x times y plus z is equal to x times y plus x times z. Okay, so we're going to assume that we have two operations, plus and times, such that, first off, when you plus two numbers together, it always gives you a real number. When you multiply two numbers together, it always gives you a real number. And these 5 properties are satisfied for plus and multiplication. The x's and y's here have nothing to do with the x's and y's up here. They're just any two real numbers. Okay. So this is just saying, anytime you add two real numbers together, you get one and only one real number. Anytime you multiply two real numbers together, you get one and only one real number. The product of any two real numbers is the same thing if you flip their order. X times y times z is the same thing as x times y times z, etc. We've been using these axioms already. Good? Nothing weird there? So he starts by introducing those first, and then he proves that he doesn't prove it. He just says, then he wants you to note, but we actually prove this. Note that Let's see how we say it. Let's start by writing his definition. So his third definition. So we have his first two definitions already listed. His first definition was a definition of a real number, or a rational. His second definition was a definition of an irrational. So now with this in mind, we have our next definition. Definition 3. And this definition is that if A is a real number, if A is any real number, comma, then B is its additive inverse B is its additive inverse, provided that what?
A plus B equals 0.
A plus B equals 0. That's what we mean by additive inverse. So he's defining what it means to be an additive inverse. So if A is a real number, then B is its additive inverse, provided that A plus B gives you the additive identity. That's what it means for B to be additive inverse, right? And then we already proved before that there's one and only one additive inverse, and we came up with a symbol for the additive inverse of A. What's the symbol that we had for the additive inverse of A? Period. We represent this, well, I don't know how I want to say that. So then, yeah, negative A, we define to be the one and only additive inverse of A. Or in other words, we know that A plus negative A is equal to 0 by definition of what we mean by that symbol, negative 8. Okay. Let's see here, negative A, negative x. Talked about that. Since negative A is the additive inverse of A, then A is the additive inverse of negative A. Okay? So, since A plus negative A gives you 0, then that means negative A is an additive inverse of A, right?
Right.
Next thing you have to notice, but notice this. Notice that negative A plus A is also equal to 0, right?
Okay.
So then A must be the additive inverse of negative A.
Yeah.
So in other words, we now know that negative A is equal to A. The additive inverse of negative A is A, since negative A plus A gave us 0. A is an additive inverse of that thing. So the additive inverse of that thing is A. You follow that logic?
Yeah.
All right. And so from this, plugging in 1 for 0, we also know that 1 plus, or plugging in 1 for A, we know that 1 plus negative 1 is equal to 0, or negative 1 plus 1 is equal to 0. So 1 is the additive inverse of negative 1, or in other words, 1 is equal to negative 1. Just a special case of that.
Yeah.
Okay. Nothing special there with the 1. And then he wants to start with, once again, reset up, since we know that 1 plus negative 1 is equal to 0. Let's see what he's doing. Then multiply both sides by A. 1 plus negative 1 times A is equal to 0 times A. Distributing through, we get 1 times A is going to be A plus, maybe I'll keep the 1 here, 1 times A plus negative 1 times A, using axiom 5 here, is equal to A times 0, we know to be just 0. Again, we proved that earlier already, but the author doesn't bother proving that. Or in other words, we can say a plus negative 1 times a is equal to 0. Or in other words, negative 1 times a is the additive inverse of a. A plus this thing gives me 0. So in other words, negative 1a is the same thing as the additive inverse of a. Negative 1 times a is the same thing as negative a. Something else that we already proved earlier.
Okay.
You follow that? Okay, with x equal to 4, just some examples. He writes to make sure that you get it. 4 plus negative 4 is equal to 0. Therefore, negative 4 is the additive inverse of that. 3. He also points out 3 is equal to negative 3 from this one right here to make sure that you get it. And once again, negative 5 is the same thing as negative 1 times 5 from here, just to make sure that you're getting it. Pretty straightforward stuff that you're already comfortable with, right?
Yep.
And we already proved a bunch of these. Okay, for any real number a, the negative of a is defined to be its additive inverse. So he's been saying additive inverse up to this point now. We've already gotten to the point where we say negative a. So now he says, when we say negative a, we mean the same thing as the additive inverse of a. That's what we mean when we say negative. Now, the author makes a note. Well, so start with any number. If I have any number a, if I put a minus sign in front of there, now you know what it's talking about. It's talking about the additive inverse of a, or negative a, right? The author also points out we can put a plus sign there if we want, and that's the same thing as just talking about a.
Yeah.
Plus a and a, it's the same thing. You with me? So the only reason that we might want to put a plus a there is because sometimes we like to talk about what we mean by a positive number versus a negative number. When I have some number, 3, 7, and if I want to make it where it's positive, I can put a plus sign there. And if I want to make it where it's negative, I put a negative sign there. Negative 37 is a negative number. When we put the plus, we mean a positive number. Nothing weird, right? Nothing weird? There is something weird? Okay.
Thank you.
And all the numbers are either positive or negative, right?
Yeah.
What about 0? Is that positive or negative? Both?
Yeah.
Neither. So every number is positive or negative with the exception of 0. Because plus 0 minus 0 is the same thing as 0. Because 0 is its own additive inverse.
Well, can't 0 be even?
Yeah.
Divided by 2.
Yes, and yes. And it's two very different questions. We're talking about positive and negative numbers, not even and odd. Every integer is either even or odd. Not every integer is either positive or negative.
Wait, so 0 is
Yeah,
0
that makes
not
sense.
positive?
No, 0 is even. A number is even, provided that I can write it as 2 times some integer. 0 is equal to 2 times what?
0.
0. So 0 is even. I can write it as 2 times something.
How do you define an odd number?
Okay, exact definitions. X is even means I can write it as 2 times some integer a. X is odd means I can write it as 2 times some integer a plus 1. Those are precise definitions for what we mean by even and odd. So 0 is even and 1 is odd. I don't know. Lots of things are even and odd. But yeah, so, and thank you for pointing this out because I noticed that was a common thing that came up in discrete math all the time. When we were talking about positive versus negative numbers, people kept mixing wires with odd and even. And I don't know why, but apparently that's a common wire mix. Odd and even has nothing to do with positive and negative. There's positive numbers, negative numbers, and zeros, and then there's even and odd. Those are two very different things. And then division. Let's see. Think about when would be a good place to stop with enough to recover. Maybe we can pick up with division next time and give us a good sense for these things. And start by going over these axioms, and then we'll reintroduce division. So, we'll call it right there. Well, actually, now I'll just give you a question. We'll end with new material there for a second, but since we did talk about the 0 being even and odd, or neither, I'll give you a question that I pondered back when I was in 5th grade, or 6th grade. I had a teacher, and the teacher, she came to me and she says, notice something funny. She says, when you have an even times an even, what do you get?
Even.
You get an even. Oh no, she said plus. If I have an even plus an even, what do I get?
Even.
And if I have an odd plus an odd, what do I get?
Even.
You still get an even. So if I add even and even, I get an even. If I add an odd and an odd, I get even. And so the only ways to get an odd is to take an even and an odd, right?
Yeah.
And so she says, so there's 2 ways to construct evens, only 1 way to construct odds. How come there's not twice as many evens as odds? How come there's the same amount of evens and odds?
So you just even and odd and then odd.
Yeah, because there's 2 different ways to do it. So I told her, because you can do even plus odd is odd, or you can do odd plus even is odd. That wasn't the thing I was stumped on, though. The thing I was stumped on is what she said in the question. Because she said, because we know that there's the same many evens as there are odds. That was the thing that stumped me. Are there the same amount of evens and odds? And I'll show you why this confused me so bad. Because if we start writing out the numbers, -3, -2, -1, 0, 1, 2, 3. So just starting with 1, you get an odd, then an even, then an odd, then an even, etc., right? So if I just start at 1 and I start counting up, do I have the same amount of odds and evens?
Yes.
So let's say up here I have the same amount. Same. You good? Then that means down here on this end, I also have to have the same, right? But then 0 is even. So then I have 1 more even than odds.
Well, it depends on.
Then I said, okay, maybe we're off. Maybe if you were to count all these, there's actually 1 extra odd. So there's plus 1 odd up here. Maybe if you count them all, there's actually 1 extra odd over here. Well, that means that there's 1 extra odd over here, plus 1 odd over here. But this is only 1 more even, so then there's 1 more odd than evens. So are there the same amount of evens and odds?
Well, numbers go on for infinity, so you can't really determine that.
Yeah.
So you can't say that there's the same amount?
Because.
So there might
if
be a
you
different
say-
amount of evens and odds?
If you say there's the same, you can then just add another odd, and then just add another even. Or just add another odd.
Is that it? You think he's right? You can't say whether there's the same amount? Some of you topology people should be a little bit wiser to this. Because I got the answer to my question in high school.
Oh, there is an actual answer to that?
Oh yeah, with calculus it was obvious what the answer was.
Oh, because you can talk about infinities.
Yeah, because then talking about infinity isn't such a tricky concept. Turns out there are the same amount of evens and odds. It turns out there are in the same way that there's the same amount of natural numbers as there are integers. The size of this set is the same as the size of this set. They have the same cardinality.
That's it.
But the natural numbers, so some of you might be confused, and you're justified to be confused, because remember the natural numbers are just 1, 2, 3, 4, 5, etc. The integers are -3, -2, -1, 0, 1, 2, 3, 4, etc. How can this have the same amount of things in it as this? How can those be the same size? Confused?
Well,
Take calculus.
yeah, not necessarily.
And you might just say, oh, well, they're both infinite. Well, let me tell you when that's not the same. The amount of integers is not the same as the amount of real numbers. There's way more real numbers than there are integers. But there's the same amount of integers as there are naturals. And it turns out that all makes perfect sense. And it can be explained to you and you can understand it. You just got to take the appropriate classes. So make sure you take my calculus classes.
Did we do that in calculus?
Anything in calculus? No, because when I say calculus, I mean real analysis.
Yeah.
I just did calculus for you guys because we can turn off the camera. I just did calculus for you guys